Hello everyone. Let's continue our discussion with MOSFET transistors. So in the last video we saw the basic structure of MOSFET. We have seen the gate, source, drain and the body terminal. We have talked about p-type substrate. We talked about diffusion regions and so on. In this video we'll be talking about electrical characteristics or the electrical properties of the MOSFET. So let's begin with one of the very important electrical property of the MOSFET, which is the threshold voltage. So by definition, threshold voltage tells us that it's the voltage at which your device turns on. So that's what the threshold voltage, the basic definition of a threshold voltage is. We'll be defining some equations, we'll be deriving some equations and giving some potential across these terminals and try to find out what this value is, what the exact value of the threshold voltage should be. We'll do all that, but the basic definition of the threshold voltage says that it's the voltage at which your device turns on. Okay, so let's continue. What we'll do is we'll try to first create a scenario. We'll try to create an apparatus over here saying that what terminal should be at what voltage. So to begin with, we'll start with the gate to source voltage. So the gate to source voltage should be equal to 0 volts, and by VGS I mean this voltage which you see across these terminals. So gate to source voltage should be 0 volts. That's the first criteria while deriving the threshold voltage. Okay, and the second criteria for deriving the threshold voltage is your drain, source and the bulk should be connected to ground. That's the second important criteria. So let's do that. Let's try to connect the source, drain and body terminal to the grounds. So while we do that, if you see, before doing that, if you observe this area is nothing but an N plus and a p-type substrate joined together, coming in conjunction together. So this reminds us of a very famous device which is nothing but a PN junction diode. You must have all learned about PN junction diode. If not, we'll be covering it in a separate set of videos, so we need not worry about that. So this reminds us of a very basic device which is PN junction diode. Even the same happens over here. You have the p-type substrate, you have the N plus diffusion region. This forms a PN junction diode. Okay, so let's move on. So the second point, what I was trying to make is we will ground the drain, source and bulk terminal. Let's do that. So this is how it will look like. You ground the source terminal, you ground the drain terminal and the body terminal. So as I said, the body and the drain will form a PN junction diode. The body and the source will again form a PN junction diode, and this diode is not connected. So let's draw the diodes here. This will make it more clear. So this is one of the terminals of the diode which is connected to ground. This is one of the terminals of the diode which is again connected to ground. Similar thing happens with this diode also. The terminals of this particular diode are connected to their respective grounds. So in that case, what will happen? If you see, in this particular case, the resistance between source to drain is extremely high. Basically, the resistance is so high that there is absolutely zero flow of current between source to drain. So that's an important observation in this scenario that we see. So the important observation is, since the diode is biased at 0 volts, both the junctions are off, and you see a very high source to drain resistance. So the job of the threshold voltage will be to make this resistance so small so that we see a current flow. That's the basic definition. We'll see how are we going to do that, but that's what we have to do. We have to reduce the resistance of the channel. So this is what we call it as a channel, the channel between source and drain. The area between the source and drain, we call it as a channel, and the name that we have put to this particular transistor is NMOS. It's N channel. So we'll be trying to create an N channel over here. So right now, currently what we have is we have the gate to source voltage over here. We have this terminal which we are going to supply some voltage. Right now the voltage at the gate is 0, the source is grounded, drain is grounded, your body is grounded. Okay, these are the observations. Your P, this forms a PN junction diode, this again forms a PN junction diode, and this particular diode are off, and hence you see a very high source to drain resistance. So these are the observations till now. Let's move on, let's move ahead, let's see what further we can do about it. So now what we'll do is we'll be applying a positive VGS, we'll be applying a positive gate to source voltage. So let's try to start with the positive. We'll connect this particular gate to a voltage source, and let's start applying the voltage over here. Let's try to make this area as positive. So there is one more observation that you see is this is your polysilicon gate, which has got a properties which is close to a metal. This is your p-type substrate, and you have an oxide over here. So there is one more device that gets forms over here, that's a capacitor. So you have this plate of the capacitor, you have this plate of the capacitor, and you have this oxide in between. So generally for a formation of a capacitor, what all things you need a dielectric, and you need two conducting plates. So P substrate is not conducting but semi-conducting. Your polysilicon gate or the metal gate, it's conducting. So between these two conducting gates, between these two conducting plates, you have an oxide. So this forms a capacitor. So this is again one more observation that we have made over here. Okay, so yeah, let's try to now what we'll do is one of the plates of the capacitor, we'll try to connect it to the positive source. Okay, and we'll try to apply positive gate voltage over here. So let's see what happens. So we have connected the gate to a positive terminal, positive voltage source, positive terminal of a voltage source. So this positive voltage source will be getting applied to one of the plates of the capacitor, which is the polysilicon gate or the metal gate. So all the positive charges will have an impact on this plate, and this plate will become positively charged. So this area of your capacitor will become positively charged. So if you see a behavior of a magnet, what does a magnet does? A magnet repels its like charges and attracts opposite charges. So similar behavior will happen over here, and let's see what does it exactly do. So you have this particular plate of the capacitor which is completely positive charged. So the first thing that you can expect over here is, so P substrate, which means there are all P-type materials over here, there are all P-type charges over here. P-type charges we generally call them as holes, and then N-type we call them as electrons. So this, since this is a P-type substrate, this is all filled with the majority charge carriers over here will be holes which are positively charged. So the direct impact that this particular positive plate capacitor will have is that it will repel all the P-type holes which are present in this area, in its vicinity. It will try to repel all the P-type holes over here towards the P-type substrate, because like charges repel. So the same property of the magnet will be getting applied over here, and you see the holes which are present over here, the positive charge particles which are present in this area will be repelled from this area. And in the process, when this particular holes leaves their position, they leave behind negative charged ions. So that's the property of a positive charge hole. So that's a basic device physics concepts that we are going to learn in some other videos. Let's not worry about that in this section. So these holes, when they move along, when they get repelled from their area, or when they leave their position, they leave behind negative charged ions. So something is in this fashion. So let's see, this positive mobile holes, when gets repelled, they will move in this direction. Let's say they move in this direction, and you see an accumulation of negative charges over here. So this is just the first layer of negative charges that you see. Okay, so the things that we have learned in this section is that whenever one of these plates of the capacitor is completely positively charged, the behavior will be just like a magnet. It will repel all the positive charges in its vicinity. It will push them towards its substrate, and in the process, while they leave their position, while the hole leaves their position, they leave behind negative charges. And just as it happens in case of a p-n junction diode, whenever the area, for example, p-n junction diode, you have the p area, you have the n area. Whenever the n area is depleted of its majority carriers, there is a depletion region formation. Whenever the p type area is depleted of its majority carriers, there is a depletion region formation. Similarly, if you see in this area, this is a p-type substrate, so its majority carriers should be holes, but this area is now getting depleted of its majority carriers, which is holes. So in that case, what will happen? There will be a formation of depletion region over here. So just consider this as the behavior of this as a diode. Same thing happens if the majority carriers, which is holes in the p-type substrate, are removed from their area, there will be a formation of depletion region because this particular area is now depleted of its majority carriers. So let's see, this is how it will look like. The depletion region will be looking something like this. So what we'll do is we have just begin the discussion on depletion region. We'll be continue with this point, and we'll see other effects also. We'll see how this depletion region gets increased and all those things. So let's try to look into all this in the next video. Thank you.